Hello everyone, this is Andrea from the Academy and Brain Boosters, and today we are going to see chapter 6. This is mechanism, limited direct execution. This operating systems 3 easy pieces. So this book is published by Andrea and Remzi in the University of Wisconsin. So let's get into it. So the first question, how to efficiently virtualize the CPU with control? This is a question. The operating system needs to share the physical CPU by time sharing or multi-programming. And here are a few challenges, because as we have discussed in the previous chapters, we have seen that the CPU achieves virtualization by the help of operating system using time sharing and using multi-programming system. So in this multi-programming time sharing system, there are a few challenges and issues in building such virtualization machinery. Okay? The first one is performance, and the second one is control. Performance means how can we implement virtualization without adding excessive overhead to the system, because we are just preemption. We have two types of process, preemption and non-preemption. Okay, so if we are preempting the running program from the CPU, okay, we call it burst time. Okay, when the process is running the CPU, we call the time it takes in the processor is called the burst time. So if we are preempting one process and putting another by the short-term scheduler, so what we are going to do, maybe the performance, the overhead will be excessive and it will be a problem. The other one is control. How can we run process efficiently while retaining control over the CPU? That is the second question. Okay, because once the process is running, then it runs for a long time. The operating system, how the operating system will take control of the CPU again? That is the problem. So control is particularly important to the operating system, as it is in charge of resource. Without control, a process could simply run forever and take over the machine or access information that it should not be allowed to access. So these are the two problems, performance and control, and it will require both hardware and operating system support to alleviate these problems. The operating system will often use a judicious bit of hardware support in order to accomplish its work effectively. So attaining performance while maintaining control is as one of the central challenges in the building an operating system. So the two big problems we have to answer in this chapter is in direct execution protocol without limit. We have two problems, as we have seen now. The first problem is simple. If you just run a program, how can the operating system make sure the program doesn't do anything that we don't want it to do while still running it efficiently? The second problem, when we are running a process, how does the operating system stop it from running and switch to another process? This implementing the time sharing we requiring to virtualize the CPU. So this is a general diagram I put, general framework, how to efficiently virtualize the CPU with control. Okay, so as you can see, we have memory, we have CPU, we have the operating system, then we have the user processes are here, first process, second process, third process. So we have an interface here now, the operating system. So how the operating system will control these processes, okay, with time sharing. So this diagram we are going to use it most frequently and in this chapter to answer these two questions, control and performance. It's very important. So as you can see, direct execution protocol is just simple. This is also from the textbook. Just run the program directly on the CPU, okay? So you have the program here and you have the operating system here. So what the operating system does, the first one is create entry for process list, because whenever there is a process, the operating system will create a process list. Second, once it gets the process list, it will allocate memory for the program, basically for the process. Then load process into the memory, okay? Load the program into a memory. Then set up stack with argc and argv, and then clear registers, then execute call main. Once the operating system perform all these processes, then it will come into the program and it will run the main function. Once the main is called, then it executes the program and return from main once it finished. Then once it finished, the operating system will free memory of the process and remove it from the process list. So this is just the direct execution protocol procedure. Without limits on running program, the operating system won't be in control of anything, and thus would be just a library. As we have seen, if the operating system doesn't have any control on the running process, I mean when the process starts running in the CPU, the operating system should have a way of stopping it, whether resuming it or killing it or terminating, whatever. But if the operating system simply create entry for the process list, allocate memory for the program, load program into memory, then set up stack with argc and argv, and clear register and execute call main. If the operating system does this, it is just a library, because that's what we don't want. So the problem comes, this is our first problem. How do we perform a restricted operation? This is the first problem we have. So what if a process wishes to perform some kind of restricted operation, such as issuing an input-output request to a disk, gaining access to more system resources such as CPU or memory. However, if we just let the process do what it wants, we will be limited in constructing desirable features like security and protection. So, what is the solution that the process is running? How we prevent the process doing this kind of restricted operation? The solution is the hardware assists the operating system by providing different modes of execution using protected control transfer. These are user mode and kernel mode. The user mode means applications do not have full access to the hardware resource, so this is just user processes. And the kernel mode, the operating system has access to the full resource of the machine or the kernel. Special instructions to trap into the kernel and return from the trap back to the user mode programs are also provided. As well, instructions that allow the operating system to tell the hardware what the trap table resides, where the trap table resides in the memory. So, how then can a user process perform privileged operation like input-output operation? It is simple. The answer is the kernel performs the operation on behalf of the user process via a system call. So as we have discussed what is operating system is an interface between the user and the hardware. So how the user benefit or use the system available in the operating system by the system calls. So this is the answer. The first problem is simple. If we just run a program, how can the operating system make sure that the program doesn't do anything that we don't want it to do while still running it efficiently? So let's discuss about the system call. The system call allows the kernel to carefully expose certain key pieces of functionality to use programs, such as access the file system, creating and destroying process, communicating with other process, allocating more memory. We'll need privileged hardware instructions because we cannot just use the ordinary function procedural calls mechanisms. So we have a lot of system calls in this umbrella. We have more than 100. So you can go to the manual page of Linux operating system. You just write man and you can see a lot of description there. So I encourage you to go there and discuss system calls, type of system calls provided in the Linux operating system. So system calls, as you can see, we have privileged instructions. So trap instruction and return from trap instruction. From trap instruction, jump into the kernel, because when the process is in the user mode, it cannot perform some IO operation or restricted operations. So when the trap instructions invoked by the system call, then what it does is it jumps into the kernel mode, raise the privilege level to the kernel mode. Example, in x86 it is usually the int instructions. In x86-64 it is syscall instructions are used. And once the process completes its task, the process, then return from trap instruction will be issued. Return into the calling user process, then reduce the privilege level back to the user mode. Then example, in the x86 it is usually the IRET instructions. In the x86-64 it is a sysret instructions. Initialize trap table, then a support instruction. So as you can see in this diagram, the x86 privilege level architecture, we have ring 1, ring 2, ring 3, and we have ring 0. So this ring 0 is the most privileged and ring 3 is the least privileged. As you can see, ring 1, the most privileged is operating system kernel, and ring 1 and ring 2 shows operating system services, and ring 3, as you know, user applications are the least privileged one, and the operating system kernel is the most privileged one. So this is a good diagram to show you what is privileged and the least privileged and most privileged in the operating system. This is just the x86 privilege level architecture. Also in the system call we have seen trap instruction and return from trap instructions in this way. So system calls privileged instruction continue. Enough information must be saved by the hardware when executing a trap in order to be able to return correctly to the process that invoked the system call. Because once the system is raised trap, then it will go to the kernel state. So when it goes to the kernel state, the progress of the process should be registered. So the hardware should register all this, the current status of the program, the process. Then when it returns from the kernel mode to the user mode, it will start from where it stopped, not from the beginning again. So the process that invoke the system, so the program counter, the flash register, other important registers should be recorded by the hardware. The information is pushed to a pre-processed kernel stack before the trap. So before the trap is issued, all the progress of the process should be put in the kernel of the stack. Return from trap will pop the information back to the register. So when the process comes from the kernel state to the user state, So what it does is all the register from the return from trap will pop the information back to the register from the kernel stack. So that is very important point. So just to discuss interrupt mechanisms in hardware, how interrupts works. If everything is going well, the CPU will just happily execute instructions, but sometimes important events needs to attention of the CPU. For example, a user process divides by 0, IO completion, a page fault happens, a system call is invoked, a timer has lapsed, or can be handled either through pooling or interrupts used in x86. Interrupts are identified by interrupt number. Interrupt classification in x86, we have interrupts. This interrupt means asynchronous hardware event, example input-output completion or explicit invocation of int instruction. Exceptions, when error condition happens, there are 3 types. We have trap, we have fault, we have abrupt. So trap means reported immediately, process continuous execution to the next instruction after trap. Example, a system call int3 debugging. Fault, reported immediately, process continuous execution to the specified fault handler. Divide by 0, this is page fault. And abrupt, several error happens, hardware component failure, kernel panic, for example BSOD, boot screen of this kind of situation. So we will see this interrupt mechanism. This is the general overview of the mechanism. So as you can see, we have trap table, and this is interrupt vector table. Just I took it from this website. And trap table, as you can see, interrupt vector table IVT, interrupt descriptor table IDT, and set up by kernel at boot time. And kernel has full privilege at this point. Kernel places in the trap table the memory address of the code, trap handler, to execute when an event generated by the interrupt and exceptions occurs, identified by the interrupt number. The kernel will set the address of the code for the system call as the system call handles to one of the user defined interrupt number. For example, Linux x86 uses 080. Exact specific operations can be invoked by passing a service number in a register or stack, thus using a number instead of address to prevent direct memory access. So I encourage you to read this point. This is the system call interrupt table. This one, as you can see, interrupt vector table. The interrupt vector table is located in the first 1024 bytes of memory at the address of this, as you can see. So divide error, single step, MIP, 1 byte breakpoint, overflow, bound, unified opcode. All these things you can go through and read it. There are 256 4-byte entries and segment and offset in the real code. So high, low, offset high, offset low. So it is there. So please go through and try to read. So the limited direct execution protocol, this is also I took it from the textbook. As you can see, the operating system at the boot kernel mode, it initializes the trap table. Once it initializes the trap table, the hardware, what it does, remember address of system call handler. Okay, so the hardware will remember the address of the syscall handler. Then once the operating system runs the kernel mode, what it does is create entry for the process list, allocate memory for the program, load program into memory, set up user stack with argv, fill kernel stack with this register program counter, Then once this happens, return from trap. When it returns from trap, so the hardware, what it does, restore a register from kernel stack, move to user mode. See, once all the register was registered in the kernel stack, then it will be restored into the user mode program, jump into the main. Then the program will start run main and call system trap into the operating system. Then the hardware will continue, save register to kernel stack, move to the kernel mode, because as you can see, when the program calls the trap, the hardware will save register to the kernel stack, move to the kernel mode, jump to trap handler. When this happens, the handler trap do work of syscall, whatever call is there, whether write or whatever. Then once it's completed, return from trap. When it is returned from trap, the hardware, what it does, restore register from the kernel stack, move to user mode, jump to program counter after trap. So once this happens, the program will return from main and trap via exit. Okay. Once it is exit, then free memory of the process removed from the process list. This is the work of the operating system. So this is the simple table. So what I want to show you, let's go to Unix now. Okay. Let's go to Unix operating system. Let's log in. So I download this code. This source code is free. Anybody can download it. And what I want to show you is download and yes, this one and mine. So let me open the terminal. Tutorial. No. Okay. Demo lawyer. Okay, wait. Download. Yeah, this one. Thank you. So open internal. Then let's see the list of programs. Yes, this we have all these programs. So let's go to change directory. Let's change our directory to here. Let me copy this one. Here. Okay. So let's see. Okay. Now let's go to change our directory to the source. Okay. So let's list. Okay. So as you can see, these are our ISR ISRH main, and we have descriptor tables, descriptor table age. So what we are going to do now, very fast, I'm going to show you, for example, view isr.h. This is our file. As you can see, this is a program isrh interface and structure for high-level interrupt service. Part of this code is modified from Remzi kernel development tutorial, rewrite, return, and as you can see, type of this is type definition of structure registers. So we have data segment selector, we have pushed by an interrupt number, error code, everything is here as you can see. So what we are going to do is quit. Let's quit, and in the same way, let's see isr.c. As you can see, this gets ISRC high-level interrupt service routine and interrupt request handler. Part of this code is modified from here. The same, we have common h, ISRH pointer. This gets called from our ASM interrupt handler, and as you can see, we have three. So let's go back. Now let's see the file descriptor. Okay, the file descriptor is table tables.h descriptors table.h. Let's see. As you can see, descriptors table h defines the interface for initializing the GDT and IDT interrupt data table. Also defined needed structures based on the code from Brian kernel development. So as you can see, you can go down the structure, you can see the low 16 in spite of the limit, and everything is here. So yeah, this one, just extract this direct list using the address of our SR handlers. So in this way, you can go and see the handlers, and we can continue. Let's see, for example, interrupt notice notice. Okay, this is the interrupt notice, contains interrupt service routine wrappers based on this, the same. So as you can see, you can go ahead and see information about the interrupt, and let's see the main.c file. As you can see, the main.c file defines the C code kernel in 3-point calling initialization, and as you can see, we have the main routine here, initializer, and you're advised to download the code. It is free source. You can do like this, and let's go back to here. So let's list okay, so we're here now. Okay, so in this way you can play around, and the codes are free. You can download it from GitHub. Okay, from GitHub, free source. So That is the first problem was handled. Now the second problem what we have is switching between processes. So when a user process is running on the CPU, this means that the kernel is not running. Assume we have a single CPU. How can the operating system regain control of the CPU so that it can switch between processes? This is a huge question. If the operating system doesn't have any control mechanism, then it will be like a library. So we have two types of methods, a cooperative approach and a non-cooperative approach. So the cooperative approach waits for system calls. Okay, in this style, the operating system trusts the process of the system to behave reasonably. Processes that run for too long are assumed to periodically give up the CPU so that the operating system can decide to run some other tasks. But this is fantasy. Maybe some program are in the blueprint, something like that. So, but it assumes like that. If the process runs for long, it will raise a system call. Then the operating system will gain the CPU again. And the non-cooperative approach, the operating system takes control. We will see it in a minute. So as you can see, the cooperative approach waits for system call. Process periodically give up the CPU by making system calls such as yield. The operating system decides to run some other tasks. Application also transfer control by trap to the operating system when they do something illegal. For example, divided by zero, try to access memory that it should not be able to access. In this kind of situation, the CPU, the operating system will gain the CPU. So a process gets stuck in the infinite loop, then you have to reboot the machine, then you will get back again. So these are the two the process by the system code and application are trapped control when they do something illegal or defect. This is operating system. Now, the non-cooperative approach, operating system take control how? The time interrupt. This is the point. The timer, a hardware component, raises an interrupt every millisecond configurable. In the x86, this chip is the programmable interrupt timer, PIT. At boot time, the kernel sets a timer handler for the time interrupt, then start the timer. During the boot sequence, the operating system starts the timer. Then what happened? The timer raises an interrupt every so many milliseconds. When the interrupt is raised, the current running process is altered. Save enough of the state of the altered process, as we have discussed. The hardware will put the register into the stack of the operating system. Okay, so save enough of the state of the altered process. A pre-configured interrupt handler in the operating system runs. The timer handler for the timer interrupt set at the boot time run code in the kernel, such invoking the scheduler to run a different process. So a timer interrupt gives the operating system the ability to run again on the CPU. This is the non-cooperative system. The cooperating system is when the program call a system call, or when they do illegal things, it will be terminated and the operating system will gain access again. But in the non-cooperative system, we use non-timer interrupt. So again, let's go to our Linux. Okay, sorry. Let's go to our Unix system. And what we are going to do, let's go here. Okay, what we are going to do, I want to go to OS 5 here, OS 5. So we have source code. Okay, let's open the terminal here. Now I want to show you, let's list the programs. These are the programs we have, and what we are going to do. Sorry. Yeah, okay, interrupts. What interrupt is? Okay, let's see this one. The interrupt. This one. Let's copy. So let's view. Let's paste it here. So as you can see, interrupts is contain the interrupt service routine wrappers. So please go ahead and read it. Yes. And the same thing, you can go ahead and see all of them. For example, which one is timer? Okay, let's see the timer. Let's see. Okay, the timer, this one. Copy. So let's see. As you can see, timer C initializes the PIT program timer and handles clock updates. And this is a program. As you can see, this is a timer. Let's go ahead and read it. The other thing, we can see the name also. Okay, let's see the name. Let's see. As you can see, defines the C code kernel entry point, cause initialization, routine. This is also the same. So all these are open source. You can go to the GitHub and you can download it, and you can play around and you can get the idea. So kernel now in control, okay, whether by cooperative or non-cooperative method, saves and restoring context. Okay, now scheduler makes a decision whether to continue running the current program process or switch to the different one. This one is scheduler. In my video chapter 5, we have seen that we have long-term scheduler, short-term scheduler, mid-term scheduler, and we have time sharing, and the responsibility of choosing which process should run in the CPU is decided by short-term scheduler with the help of the operating system. So if the decision is made with the switch, then the operating system executes context switch. Okay, it will take the process and it will context switch will continue. So what is context switch? A low-level piece of assembly code save a few register value for the current process onto its kernel stack, because when the current process is running, the progress of this process should be stored where in the kernel stack. So what is the information? General purpose registers, program counter, and kernel stack pointer. These are the 3 points which will be recorded. Then restore a few for the soon to be executed process from its kernel stack. So when this process is removed from the CPU and the soon to be executed will come again, the stored progress will be restored. Then switch to the kernel stack for the soon to be executing process. By switching stacks, the kernel enter the code, the context switch code in the context the interrupted process. returns in the context of the soon to be executing process. The main idea is the progress which is stored in the kernel stack should be restored for the soon to be executed process. As you can see now, limited direct execution protocol, timer interrupt is here. As usual, as you see, the operating system at the booting time, it is in the kernel mode. So what it does is it initializes the trap table. So when it's initialized trap table, the hardware, what it does? Remember addresses of the system call handler, timer handler, IRQ0, interrupt request timer 0 line, start timer, then interrupt CPU in microseconds, okay? This will be handled by the hardware. So once it starts interrupt timer, so there's the start timer interrupt CPU in every microsecond. So as you can see, the timer interrupt saves the register of the program counter, the process counter A to the kernel stack of A, okay? From the counter, from the register, the program counter into the kernel A. Move to the kernel mode, jump to trap handler, okay? Then this happens when the program user mode process A is already in the user mode currently. So what happens? It will continue, then the handle the trap, whatever trap called, call switch routine, then save a register program counter A to program counter structure, the process structure A, okay, from the stack into the process structure of A, PCB. Then restore register of program counter B from the process structure B, switch to kernel stack of B. So from here, return from trap. When it return from trap into B, then the hardware, what it does, restore register program counter of B from K, kernel stack of B, then move to user mode, jump to B's program counter, then process B will continue. So in this way, that's what it does. So this is XV6 context switch code, void switch structural code. As you can see, save current register context in old and then load register context from new. So as you can see, put old into EX, and this is the XV6 context switch code. This is from the textbook also, and if you want to see it again, let's go to here. Let's log into our Unix system. Okay, now in this time, let's go back, and what I need is I download all the codes, and here I think this one is XP6, yeah. Okay, this one here. So what we do, let's open in terminal and let's restore the program here. As you can see, all the programs are here. So what I want to show you is now switch S. Where is the switch? This one. Let's copy. So let's view switch. So as you can see, this is the switch. So if you want to read what you need, context switch. Okay, this is a context switch. This is the same as what I've seen. The other thing, yeah, that's what I wanted to show you, because the code, this is the code, okay, the switch. So as we have seen now, this is the switch code. So download the code from the GitHub and you can realize that. So at this point, note that there are two types of register or save and restore that happen during this protocol. Okay, the first is when the timer interrupt occurs. In this case, the user register state of the running process is implicitly saved by the hardware because they interrupt using the kernel stack of that process. Okay, but the second is when the operating system decides to switch from A to B. In this case, there is no timer. In this case, the kernel register state is explicitly saved by the software, such as the operating system. So no need the hardware and the kernel stack, okay? But this time into memory in the process structure of the process, okay? So no need in the kernel stack, I think. But the kernel stack, the hardware is responsible to save the running process state when we use interrupt, okay? Time interrupt. And it will be stored where? Kernel stack. But in the time of when the operating system decides to switch from A to B, what it does is, this time it will be saved into the memory in the process structure of the process itself. So it's very good point. The later action moves the system from running as if it just trapped into the kernel from A to as if it just trapped into the kernel from B. So this is a very important point, because when the process context switch happens in the using time interrupt in a non-cooperative system, or in the second time when the context switch happens by the decision of operating system, where the register will be in the kernel stack or in the memory of the process structure. This is very important point. So worried about concurrency. Now, what happens if during interrupt or trap handling another interrupt occurs? This is the question which was raised in the book. Okay, kernel handles the situation. The first obvious solution is disable interrupts during interrupt processing. Okay, this is the main idea. If you just disable the interrupt, though, you will not face that problem. In the x86, use the CLI, clear interrupt, and STI instructions. Use a number of sophisticated locking, like semaphores. We will see it in another chapter. Seems to protect concurrent access to the internal data structures. So this lecture slide set was initially developed by operating system course in computer science at Halo Academy and Brain Boosters. This lecture slide set is for OSTP book written by Remzi and Andrea at the University of Wisconsin. And today we have seen chapter 6, and I hope this was helpful for you. And I'm Engineer Selassie from Halo Academy and Brain Boosters. Next time we will come with another video. For now, bye bye. Thank you.